So if the shear stress known, we can actually find the torque of the shaft. What does it mean? Okay, so if you remember, the torque, okay, T is equals to force times radius, right? So the force itself can be represented by 2 pi r L and then the shear stress. Okay, so if you were to look at the SI unit, the torque is Newton meter, and then the and then 2 pi r, this component is only meter because only radius has a meter, while radian is there's nothing, it's just some pi, that's all, just some values. And then L itself is the thickness of the shaft, so it's a meter. And then torque, okay, this is not torque by shear stress. Shear stress is Newton per meter square, right? So therefore, we can actually cancel out. You have Newton times the radius, which is meter. So end up, this is cancelled. So Newton meter. So this is a general quite neat of a formula. And then this thickness is thickness of the shaft. Okay. So what does this mean? Okay, is that you have this shaft over here, and then you have the bearing, and you have the fluid flowing, right? So you have a fluid flowing in that manner, right? Then you have your velocity profile, right? And then okay, and then the thickness is actually this one. So this is the thickness. Okay, this is the thickness. And then yeah, and then the radius of the shaft is actually this radius over here. That's all it's saying, right? And then okay, so with this understanding, we can actually just sub in our shear stress. Okay, because the only unknown is the shear stress. The rest is given. Okay, if you can measure, you can measure. So we just simply take the shear stress formula. So this is the same as this one, right? I didn't cheat your feeling. So this piece over here, if you were to bring all the way up here, okay, they are the same formula, right? They are the same exact formula. So okay, where am I? So what do we do next? So now you have to assume that the top of the shaft is at when y is equals to a. So why do you say so? Okay, when there is a spinning, okay, this is the force, the top force should be spinning in this another direction, so maybe cancel. So we have spinning in this direction, so the force is spinning in this direction. So the top force is trying to pull this thing in a circular motion, okay, going in a round and round and round motion, in an anti-clockwise motion. And then the top of the shaft is normally generated at the because mostly the contact point is the contact point of here to the fluid itself. So this layer is where the velocity of the fluid is the fastest, and then slightly slower and slower and slower. Then you have a velocity profile over here, right? If you don't understand what I mean, you should go back to the very first few part of the video. Okay, this is the shaft that is turning. So this is the velocity profile, and this is the layer by layer stuff. So this is what I'm doing here. So this is exactly the same thing. You can also draw over here. So assume this is the plate, right? Then you have the velocity profile. So this is what I'm doing right now, right? And therefore, so the force, the top force, the top force, the highest top force is actually through here, right? The contacting point to the fluid. So because the fluid itself experiences friction, while yeah, so the highest torque you can achieve is actually at this point. At this point, there will be no. It is the torque itself. The torque power itself is pretty much minimum because the velocity is very slow over here. Okay, so yeah, with this said, this is just the meaning of it. So the top of shaft is at when y equals to a. So a is at this point, right? So this is the y axis, and this is when y equals to 0. This is when y equals to a. So this is what it means. And then so I just sub in my y. Okay. So what I did earlier was I have my top formula, force times radius. Okay, and then I sub in my shear stress, and then I say that y is equals to a. Therefore, I sub y equals to a. So 2a minus a you have. Nonetheless, this one will become a, right? Because 2a minus a is a. So therefore, you have partial p partial x, a over nu. Okay, so this a over here, a over nu. So this is the same as this. U over is the same as this. And then this is the nu. Okay, this is the same as this. L is the same. 2 pi r times r. So it's 2 pi r squared. So this is the description of the torque force. So I'll see you in the next video to derive power, and then also to derive the volume flow rate Q. I'm actually making longer videos than 2 hours, but hopefully this explains a lot of things. So I'll see you in the next video.